So I'm Carsten Beyer, so I'm system administrator at DKRZ. So we are just around here the corner, a kilometer away, non-profit company or limited company since 1987. So we have some public shareholders from Max Planck Society, town of Hamburg, and some parts of the Helmholtz Society. We're about 100 people. So our current system is called Levante, built on Atos Sequana, approximately 2,800 nodes. So we will extend this the summer again. So yeah, we have additional 60 GPU nodes with NVIDIA, the AI100. So attached, nearly 130 petabyte of disk storage. So these are the three file systems we have in the moment. So it's home, so 100 terabyte NVMe. We use it for our home directories and our software tree. It's most times small files, fast access. Then we have our large file system called project. So it contains the project directories for our climate projects, about a little bit more than 300. So we use also Lastro project quota. I will come later to this. And it contains also the scratch directories for each user. Then we have something that we call currently fast data. So it's hybrid storage with 200 terabyte NVMe and 3 petabyte disk storage. And there we have a collaboration with DDN for testing new workflows and concepts for our system and our works. Additionally, we have a tape archive with about 80,000 slots. 10,000 are remote in Garching near Munich. So 158 petabyte of climate data. The increase was only 25 petabyte last year because we have also a new HSM system. So it could be more because we have more than 700 petabyte capacity. So this is more from our application side. So on the left side, you see simulated clouds with an 80-kilometer horizontal resolution and the new icon SRESM with a 2.5-kilometer resolution. So this is a challenge for us because one simulated year per day on a 1-kilometer grid. So it becomes more and more horizontal grid points and just the atmospheric part, with 90 levels and 10 different variables. So that's why we need a lot of petabytes of storage. So this is an interactive analysis of data. So on the R2B9 global mesh, so it's 5 kilometers. So it produces 195 terabyte per 1 year simulation. But climate science started at 3 decades of simulation. So a single experiment is then 6 to 10 petabytes. So that's why we need fast and smart data formats. So this next GEMS is something that will start next week, so a hackathon, where will they try also some new features of what we are currently trying. So in addition to everyday challenges from application view, so from the classical parallel I/O, we are going more to Python-driven formats and approaches, so like ZAR and S3. So it's often easier data handling from our user perspective, but that requires other new system layout because what we saw currently now, 300,000 subdirectories, millions of small files. So we are thinking of some kind of limitation like QoS on the InfiniBand, because we have sometimes some toxic I/O traffic, and to separate this from the usual MPI communication. Also thinking about isolating toxic I/O from specific users when they do something nasty. We have also some kind of shared nodes where they do things, so we have separated these currently. So yeah, that's the thing. For the fast data file system we have for testing, we are trying now the hot and cold pooling on the NVMe and HDD part. So it's 200 terabyte NVMe, it's a hot pool, and 3 petabyte disk space as cold pool. So as I already said, this NextGEMS hackathon, we are currently writing the data to our large file system, so we have to copy it. And then we will see how this could improve the workflow with often accessed data on the hot pool, low or not accessed data on the cold pool, and automated two-way migration between both pools. So one of our challenges last year was, because our user requested that, to copy about 45 petabyte of data from one system to the new one, and we decided to do that without LNet routers. So with DDN and ATOS came up the idea of creating a second IP network on the InfiniBand interfaces of all storage servers. On that, creating a new TCP LNet, a new routing, and that then we were able to mount on the old system via 2 InfiniBand gateways the new file system, and then it was about 2 months copying. It was a parallel copy tool wrapped in Slurm jobs, project by project during production, but it was sometimes hard to keep them in sync. But in the end, we made it. So other challenges, because we have this Lustre project IDs on the large file system. So for each climate project has a unique ID, quota, limit enforcement. And also all the scratch directories have this quota ID for the users. Users cannot move data anymore, even if they are in different projects, because the MV command does not working anymore like it should be. So now we make some manipulations then for large data sets that we tweak the quota ID on the source directories with the ID of the new ones, and then it's a metadata operation again, and it's pretty quick. And setting the Lustre quota ID is also pretty quick recursively. We had some requirements in our procurement for snapshots, so it was installed, but it's currently not usable, so we wait for a newer exascalar version to use it, and we will see. And we had another requirement because we are using the Lustre outside of our HPC cluster on VMs or servers, and some of these have services sometimes also exposed to the internet, and with the node map feature, we can enforce it like in NFS, that it could be only mounted read-only. So that makes things for us much better. So we have also to do some statistics for our project administrators, and on the previous system we used Robin Hood. So, but since the system is growing and getting larger, so we are now went on to the Lustre integrated policy engine. So once per day we are scanning the metadata servers. And after that we are just running a small Slurm job with some Python analyzing this JSON output. So the runtime of the scan is up to 8 hours in the moment because we have 8 MDTs, but the data is not equally distributed because we had an extension with some more MDTs, and so it takes about 4 hours on a single CPU to analyze the currently 1.5 billion JSON lines. But the good thing is we don't need any new or any extra hardware like as for Robin Hood. So that was pretty fast. So any questions, and thank you.
Any questions for Carsten? No, thank you.
What?
Oh, yes, there is a question. Here, hold on.
I have to admit that I didn't focus all the time properly, but I still didn't see what was the home directory file system that you are running.
What?
File system for the home directory, since you have a Lustre or no?
Yeah, we have, this is all Lustre.
Okay.
It's all Lustre.
Okay, thank you.